Electrostatics is the study of electric charges at rest. You've seen its effects before. Clothes sticking together, a balloon clinging to a wall, sparks after walking on carpet. All of that happens without contact, which tells us an invisible force is acting through space. That force comes from electric charge. Charge is a property of matter, and it comes in two types, positive and negative. Like charges repel, opposite charges attract. Charge is measured in coulombs, and it's conserved, meaning charge isn't created or destroyed, only moved around. Now the key question is this: if two charges interact, how strong is the force between them? That's what Coulomb's law answers. Coulomb's law says the magnitude of the force between 2 point charges depends on three things: the size of each charge, the distance between them, and the fact that the force spreads out in space. Mathematically, the force equals k times the product of the charges divided by the square of the distance between them. The 1/r² part means the force drops quickly as charges move apart. Double the distance, and the force becomes 4 times weaker. Force is a vector, so direction matters. The force always acts along the line connecting the charges. If the charges have the same sign, the force pushes them apart. If they have opposite signs, the force pulls them together. Newton's third law still applies. Each charge feels an equal and opposite force. Coulomb's law works well, but it hides an important idea. A charge doesn't wait for another charge to show up before doing anything. A single charge changes the space around it. To describe that, we introduce the electric field. The electric field tells us what force a charge would feel at a given point in space. It's defined as force divided by a small positive test charge. The direction of the electric field is the direction a positive charge would be pushed. The field exists whether or not a test charge is actually there. For a single point charge, the electric field comes directly from Coulomb's law. The field equals k times the source charge divided by the square of the distance. A positive charge creates a field pointing outward. A negative charge creates a field pointing inward. Once you know the field, the force on any charge is simple. Force equals charge times electric field. Electric fields are vectors, so when multiple charges are present, their fields add together. This is called superposition. Adding fields is often easier than adding forces, which is one reason fields are so useful. To visualize fields, physicists use electric field lines. The arrows show direction. The spacing shows strength. Lines start on positive charges and end on negative charges, and they never cross. The lines aren't real objects, but they make the geometry of fields easier to see. Finally, there are limits. Coulomb's law and electrostatic fields apply to charges at rest. When charges move, magnetic fields appear, and the full description requires electromagnetism. But as a foundation, Coulomb's law and electric fields explain how charges interact and how forces act through empty space.